So this video is on bond enthalpy. It has to do with how far atoms are when they form a bond, how much energy is released during the formation of the bond, also how much energy is going to be absorbed if you want to break that bond. And so what you have to do is look at this graph and look at the axes very carefully. On the y-axis, you have the potential energy in kilojoules. Positive would be an endothermic process, negative is an exothermic process. So we clearly know bonding is an exothermic process. That means energy is going to be released during the formation of the bond. On the x-axis, you have internuclear distance. And on the right-hand side, things are very far apart. So I erased that. Okay. On the right-hand side, things are far apart. And on the left-hand side, things are going to be close together. All right. So when atoms are very far apart, there's zero, zero, zero potential energy associated with them because they're not interacting at all. But when they get closer to each other, what happens is Coulombic forces start to take over. The positive nucleus of one hydrogen atom is now attracted to the electron of the other one, and vice versa. And the example we're using here is two hydrogen atoms forming a bond. Okay, so there's Coulombic force of attraction as the atoms get close to each other, right? And that means as things get close to each other, energy is going to be released. So as the internuclear distance decreases, as we move in this direction, the potential energy is going to start to drop down. That means energy is released because these atoms are going to be bonding with each other. And it keeps going down as they get closer and closer to each other because of the attractions of each nucleus for the other atom's electrons until it gets to a certain internuclear distance that is the standard distance between two hydrogen atoms. Now, are they always exactly that amount? No. Okay, atoms move, they vibrate. However, that is the most stable internuclear distance. And the reason why that's the most stable is because there is a balance between the attractions that we just talked about of the nuclei of each atom for the other one's electrons, okay, and repulsions. Because as atoms get closer and closer to each other, the nuclei, they can't get too close to each other. There's a certain, right? And so if you look at the graph, the standard graph goes like this and goes up, 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 and then there's just like an arrow at the end, right? Because as the nuclei get closer and closer to each other, they repel more and more. And so the amount of energy that would be required to cause them to actually fuse is a huge amount of energy. That's why we don't see a lot of nuclear fusion going on except in places like the sun where the pressure is very, very intense. All right, so this is showing you repulsions over here. Okay, and it's between those two nuclei and also the two electron clouds to some degree. Okay, so they are now repelling each other. Okay, because like charges repel. Now, summing this page right here. Okay, there's a certain as the atoms get closer, energy is released. This is the internuclear distance where there's a balance of attraction and repulsion. Okay, the attraction for the nuclei for the electrons of the atoms, and the repulsions of the nuclei for each other as they get too close to each other. All right, and because it's a negative value, we know that the process of forming this bond would be exothermic, and the process of breaking it would be endothermic. If we look at a bunch of different diatomic molecules, okay, we should understand how the diagram is going to be a little bit different. Let's talk about hydrogen first. Hydrogen only has one valence electron. So in general, hydrogen atoms are going to have a shorter, okay, internuclear distance than these guys over here because these guys have two energy levels. Now, what's important to recognize here is a single, double, and triple bond, all right? Triple bonds tend to be shorter, and the bond enthalpies tend to be greater. So if I were to do two diagrams, let's see, and I'm going to draw one and then erase. Like let's say I would put like fluorine on here. Now fluorine is a slightly smaller atom. It's got a greater nuclear charge. Okay. However, it only forms a single bond here. So it's going to have an first of all, if this was where the hydrogen was, okay, the internuclear distance for fluorine might be here. And so if this is like 0, it goes down like this, and it goes down a little bit and up like that. Okay. If I were to then compare that to, let's say, oxygen, right, because of the double bond, right, and I'm going to change color here. I've never really done that on one of these items. Let's make it red so it stands up. I do now. Going back. Sorry about that. If I were to do oxygen instead, it'd be kind of the same diagram, except it would go further because they're going to get closer, and it would go deeper because a double bond involves a release of more energy. It's more stable. So the oxygen bond and double bonds are shorter. So this bond here is both shorter, okay, and the formation, it has greater bond enthalpy. And that means more energy is released during the formation, and also means more energy would be required to break it. All right. And if I were to then go to, let's say, nitrogen, all right, and do the same thing, nitrogen is going to start at zero just the same way, except it's going to go even further to the left and further deeper down. However, and hydrogen would not go as a single bond, so it wouldn't release as much energy during the formation. Okay. Um, but it would still have a shorter internuclear distance because it's just a tiny atom. So you have to take into account both things. They tend to do comparisons of atoms that either have different numbers of energy levels and the same number of bonds, which means the one with less energy levels would have the shorter internuclear distance, okay? Or comparing atoms that are double bonds, triple bonds, which have the same relative radius. So that'd be like oxygen and nitrogen. Recognize nitrogen because it's triple bond would be the atoms would be closer to each other and the energy release would be greater. And you can see this illustrated in this diagram here. So this is a diagram of bond energies, all right? And we used this earlier in the year. This is sort of a review thingy, but it's associated with bonding and it's on the worksheet. And so there's a couple questions on this. So when you're doing something like this, what you really want to do is recognize if you have, for example, a combustion reaction where methane is reacting with oxygen to make CO2 and two water molecules, and I balance the equation so this works out, that whenever you break one of these bonds, okay, that amount of energy is going to be absorbed. This is an endothermic process. Whenever you form a bond, it's exothermic. So delta H, right? Oh, I don't know how I just did that. All right, here we go. So delta H can be attained several ways, okay? If you're given the H of formations, it's products minus reactants. But when you're doing bond stuff, since the breaking of the bonds is always endothermic, you're going to make the bond breaking endothermic. So the reactants are going to all be endothermic, and the products are going to be exothermic because of the bonds that are going to form. So in CH4, there's 4 CH4 bonds. You're going to do like 4 times this number, okay? Plus 2. Now there's one oxygen, so there's just like one of those. That's endothermic. Now there's 2 of these C double bond O's, and they're down here, by the way, in the chart, okay? And so we're going to make 2 of those, but we're going to negate those because those are the bonds that are forming, so energy is going to be released during their formation. It's very important you have a balanced equation. You carefully count up bonds. So while there's 2 of these HO bonds in the water molecules, since there's 2 water molecules, we're going to form 4 of those bonds. So there's going to be like 4 times that, and that's negative. I'm going to pause this and get my calculator. I'll be right back. So that gives me a total value of negative 1319 kilojoules, okay, as per the reaction as written. A quick pointer that sometimes helps students is to realize when you're doing these things, if the bonds are still there when you're done, don't count them. So if I was going to do, let's say, by the way, this is the overall delta H for that reaction. If I were to do this one up here, all right, and I got to move it small so you can see it. All right, you'll note that this bond, this bond, this bond are still there at the beginning and the end. So if I want to figure out the delta H for this reaction, there's no point in me including the bonds that were there at the beginning and there at the end. The easier thing is just to focus on the bonds that were broken and formed during the process. So essentially, if I'm doing this one right here, I look up Br2, which I see I have at 193. That's good. Now I'm going to break that bond, one of them. It's a balanced reaction. And then I'm going to form one of these CBr bonds, which I found right here, 276. So it's going to be like minus 276. And I'm also going to form an HBr bond, which is right here. And so it's going to be like minus 363. And I'm going to get a value for that. I'm going to pause again and break out my calculator. And so I get negative 446 kilojoules for that. Notice I just ignored those ones that that don't break or form during the process, right? Little information that's going to show up later that I thought I mentioned now during this video is when you deal with something called resonance. So when you're doing molecular structures, like this is a nitrite, okay? That's the molecular structure for this. This is often written in like 2 ways. So it's written sort of like with a double arrow, and then they put a bracket here, okay? And they put an N here and an O here, and then they do the whole thing. All right, with a -1 on there again. And the idea is something called bond order. So if they involve this nitrite ion in a chemical reaction, which the nitrite ion actually breaks, what they'll talk about, and it's sort of a way of telling you something when you're doing a Lewis structure, they'll tell you that the bond enthalpy is somewhere between, let's say, it's like half. If they say the bond enthalpy for the bond between N's and O's, and they don't tell you what the bond is, like it's not telling you it's a single or double bond, but they say, oh, it's about 400. What they're telling you is that basically this is a resonance situation, a situation in which there's a double bond on one side, a single bond on the other side, but the second bond actually, they say it resonates. And what that means is that second bond essentially is a delocalized pair of electrons. And that means it's in both places at once. And so what they say is, see how you have one bond on this side and two bonds on that side? They'll say the bond order here is like 1.5. What they did was they took the three bonds there and they divided it by the two spots. And what that means is about 1.5 bonds per spot, which means the enthalpy for breaking that bond, the amount of energy required to break that bond, would be about 400 kilojoules, or halfway between that of a single and a double bond. If you were dealing with a nitrate, which is like this, it has a single bond, and a double bond. I'm not going to bother with all the extra electrons, okay? The bond order for this one would be like 1 plus 1 plus 2, and you would say, oh, that's equal to 4, and there's 3 spots, so the bond order would be 1.33. And what that means is the enthalpy associated with that bond would be closer to that of a single bond than of a double bond between the N and the O. So the bond enthalpy might be something like 300 kilojoules per mole. All right. This is usually given as information in a question to guide you towards the realization that this is a resonance situation, that the bonds, that there's like either a double bond on one side, a single on the other, or something, some mixture of bonds there like that. You'll see this later on, but I wanted to bring it up now while we're doing bond enthalpy. So quick summary, when bonds form, energy is released. The internuclear distance that is the lowest energy is a balance between repulsions and attractions. Whenever you make a bond, energy is going to be released. It's always exothermic. Whenever you form bond, energy is released. Whenever you break a bond, it's an endothermic process and energy will have to be absorbed. You can use the bond energies to figure out the overall delta H of a reaction. Make sure that the bonds that are broken are always endothermic and the bonds that are formed are always exothermic when you're adding them together. Products are bonds formed, reactants are bonds broken. And finally, if the bond energy is somewhere between that of a single and double bonds, that's probably because it's a resonance situation in which one side you might have a single, the other side double, and really it's 1.5 bonds because the second bond there is a delocalized bond and it's found on both in both positions simultaneously, and we'll talk more about that later.